This is, in the end, what we get when light goes through two openings, diffracts through both openings. The overlapping diffraction patterns interfere with one another and produce this interference pattern. We know that in between the screen with two slits, the barrier, and then the screen that detects this interference pattern, we know we get all kinds of stuff going on. We know we get an area of constructive interference, another area of constructive interference, another one, and another one, and another one, and so on. And then we know that in between all those, we get areas of destructive interference. If this represents a water wave, then we can see these areas of constructive interference and destructive interference just fine, just by looking at them. But if these are light waves, we can't see them because they're not reflecting off of anything. So as far as we're concerned, it looks like they're not even there. So we have to introduce a screen to detect it. This is our screen. This screen as soon as I get rid of that, there you go, this screen ends up forming a bright spot right here, which corresponds to that line of constructive interference that we couldn't see through the air. And then we have a dark spot beside it, and then we have a bright spot, and then we have a dark spot, and then we have a bright spot, and so on, corresponding, again, to these areas of constructive and destructive interference. That's what we want to look at here, are these bright spots and dark spots on this screen. What's another name for a bright spot? A maximum. Bright spot or a maximum. What's another name for a maximum? Antinode, an antinode. So bright spot, maximum, antinode, constructive interference. What's another name for a dark spot? Node, minimum, destructive interference. Okay, I don't really care what term you use there. Just be prepared to see all of those terms. Recognize that they all mean the same thing. All right. Let's identify, again, what some of these variables mean in this equation here. Lambda is the easy one. That represents wavelength, and that's usually visible light, which would mean it's usually 10 to the minus 7 meters, which corresponds to 10 to the 14 hertz. Right? Let's look at d, little d. What does that stand for? Distance between the openings here, distance between the slits, from the middle of one to the middle of the other. And that's going to be, in the context of one of these courses involving visible light, that's always going to be a really, really small distance. Okay, if we're talking about water waves with a much bigger wavelength, then you might have a distance between those slits that would be bigger. But in the context of light waves, that's always going to be a really, really small number. What does L mean? Lowercase l here, I label it as an uppercase L in the picture. Yeah, it's this one right here, the distance between the slits and the screen. And that's going to be a bigger number for sure, a bigger number than little d. What about x? This is the one that starts getting a little bit tricky here. X is a distance, okay, not a number, it's a distance measured in meters from one maximum or minimum to another maximum or minimum. So in other words, it could be from here to here. It could be from here to here, whatever. Okay, it doesn't really matter. From one max to another max, or one max to a min, or one min to a max, or whatever you want. As long as n is consistent with it. N is a number. X is a distance in meters. N is just a number. It's kind of like saying, okay, Leah is a bright spot. Okay, I'm a bright spot. Okay, Jackson would be a dark spot in between the two bright spots. Okay, the distance between Leah and I would be about 2 meters. Okay, that would be X, 2 meters, the distance between us. But yet we count the floor tiles, 1, 2, 3, 4, 5, 6, 7, 8, 8 floor tiles. Okay, that's a number. That would represent N. So N is a number, 8. X would be the distance, 2 meters, between those two maxima, or those two bright spots. All right, what would N be in this case? Let's assign a number 0 to this, 1 to this, 2 to this, 1 to this, 2 to this, so on, right? This is from 0.5 to 2, so N would be? Subtract the 2, it's going to be 1.5, right? It's the difference in max or min number. What about the next one here? We're going from 1 on one side to 1 on the other side, n will be 2. Now, we say that it doesn't really matter what value of x you use, as long as n is consistent with that. Realistically, when you get a problem, you're going to be given one value for x. So even though Jackson could use a different value for x than Christian used for x, as long as they were consistent with the values of n, realistically, they're going to be both given the same number for x, right? When I say that you can use whatever number you want, like we're talking experimentally, Jackson may measure one value of x, Christian may measure a different value of x, and that's okay as long as Jackson's n is consistent with his x, and so is Christian's. Okay, does that make sense? All right. What about theta? What about this other one, theta here? Yeah, it's an angle. Angle from what? Yeah, x is from anything to anything, basically. Theta is measured, an angle, measured from the central max to some other maximum or minimum. So here we would say theta, the angle between the central max and the second order maximum. Here we would say that theta is between the central maximum and the second order minimum. What would n be in the top one here? Central max to the second order max, n would be 2, right. It's 2 minus 0 is 2. And what about the next one here? From the central max to the second minimum, first minimum, second minimum, n would be 1.5. So once again, as long as you're consistent, n can be, or theta can be whatever you want, as long as it's measured from the central maximum and n is consistent with that. Yep?
Just to clarify, you have to use an angle from the center, like say if you
Yes.
from like the top max to the bottom max, you have to divide that by 2.
Well, you'd have to be really, really careful with that, actually. When you're using theta, it has to be measured from the central maximum. So if you're going from the top one to the bottom one, say the second on one side to the second on the other side, you actually couldn't use that equation without splitting it. So what you do is analyze this, and then analyze this. You're not going to have to do that. Okay? If you've got two maxima that are not, and one of them is not the central maximum, you're going to use the other equation. Okay? Realistically, that's just what it is. Like, it is conceivable to use the d sine theta equation. It's just that you're not going to do that. Okay? Now, we do have a big if beside this one. What was the big if? Yeah, this is an approximation, right? This equation is an approximation. This one is exact, like it's perfect. The bottom one is an approximation if the angle is pretty small. If theta is less than 10 degrees, it's not perfect, but it's a good approximation. And the answer that you get will be good enough for the diploma exam people. If the angle is bigger than 10 degrees, they won't accept the answer that you get from that equation. You will have had to use the other equation. Now, we know that if we draw this out here, even if we're given the value of x and L, let's say we've got a maximum. This is my central maximum. Okay, and we're going from the central maximum to the third order maximum. This would be x, right? Even if we have that value of x and we have the value of L, we can find theta every time. We can find theta by saying tan theta is equal to x over L. We can find theta to determine whether it's bigger or less than 10 degrees, and therefore determine whether that equation is valid or not, right? But if you find theta every time between 4 and 0 or between 2 and 0, whatever, then why wouldn't you just go back to using this equation? Like, that's the thing. Like, there's virtually no point to having that second approximation if we're always going to find the angle to see if it's bigger or less than 10 degrees. So what I'm suggesting you do, what I suggested you do yesterday, and I'll remind you of that, is to do a little test, a little rule of thumb. Ask yourself, is L greater than 10 times x? If the answer is yes, then the angle will be less than 10 degrees every time. Now, if the answer is no, well, the angle could still be less than 10 degrees. It might still be less than 10 degrees. But if it is, even if it is, and you have to calculate theta and you see that it is still less than 10 degrees, there's that one time out of 10 when the rule of thumb forced you into doing this, as opposed to We're not using the rule of thumb 10 times out of 10, having to see if the angle is less than 10 degrees. Does that make sense? So check the rule of thumb. Okay, 9 times out of 10, L will be greater than 10 times X. If it's not, then find theta. And then once you find theta, if it's less than 10 degrees, you can still use this equation if you want. If not, then you've got to use this one. All right? All right. We had 2 example questions yesterday. Example number 1, example number 2. And we're left with 4 questions on worksheet number 19 that I'd like to take a look at here now. All right, let's have a look at questions 2 and 3 on that worksheet. Number 2 says the distance between the first order maximum and the third order minimum is that value. That's X, right? The distance between max and min is X, 6.17 times 10 to the negative 2 meters. As soon as we write down a value of X or theta, remember that n has to be consistent with that, so let's get n right away. We wrote down X, let's get n right away. The central maximum to the third order minimum. Okay, here's my central maximum. First order maximum on one side, second, third, fourth, and so on. We're looking for central maximum and third order minimum. 1, 2, third order minimum. What's n going to be equal to? Not 1.5. Central max to third min, or you could think of the third min as the 2.5 max. We'd say n is 2.5. Okay, good. Let's go to the next one here. It says the slits are 2.5 times 10 negative 2 meters apart. That's little d. Sorry to make a mistake?
It's 1.5 because it's from the first to the third, not the second.
Oh, yeah, you're right. Yeah, it's the first to the third minimum. Yeah, first maximum to the third min. So first maximum to the 1, 2, third minimum, n would be, you're right, thank you, was 1.5. The other variables, I think, are right. We're looking for the wavelength here. Okay, we're going to say lambda is equal to, looks like xd. Oh, wait a sec. We have something else here, right? L. Lambda is equal to xd over n times L, right? Looks like it fits, right? Now, I'm going to let you in on something here. Like, technically, we should do a test here. But the reality is, since you're not dealing with the central maximum, you're not going to use the equation with the angle. Like, it's just not going to happen. So you can probably avoid even doing a test on this. Does that make sense? Now, in the end, if we did do the test, like, we can do it, and we can justify that, sure enough, this equation is valid. Okay, is L greater than 10 times X? L is 1. 10 times X is 6.17 times 10 to the minus 1. Is L greater than 10 times X? It is. Yeah, it is. So we are allowed to use that equation, right? I'm telling you that, like, it's conceivable that when you get a question involving the first max and the third min, it's conceivable that that equation won't be valid. But it's not going to happen. Because in order to use the other one, you need to know the angle from the central max, not from the first order maximum. Does that make sense? So theoretically, it's possible. In practice, it isn't going to happen for you guys. Okay? So this will be valid. Lambda is equal to 6.17 times 10 to the minus 2 times 2.5 times 10 to the minus 2 divided by n, which is 1.5, times L, which is 1.0. When we do this, we get 1.03 times 10 to the minus 3 meters. Number 3, how far apart are the slits on a diffraction grating if the third order maximum is seen 25 degrees from the central maximum when using light of wavelength 630 nanometers? What do we got here? What are we looking for? How far apart are the slits on the diffraction grating? d, little d. Third order maximum, 25 degrees from the central maximum. So theta, we're allowed to use theta if it's measured from the central maximum, right? This one is 25.0 degrees. Listen, we know right away that that second equation would not be valid here. We couldn't use it. But listen, why would we want to try? Like, why would we want to even bother, right? If we have theta measured from the central maximum, like, why would you bother using the approximation when you can just use the one that always works? All right, we got theta. We do have to have a value of n that's consistent with that. As soon as we get x, or as soon as we get theta, then let's get the value of n that is consistent with that here. Let's draw it out. Sometimes it's useful to do that. Central maximum, first on both sides, second, third, fourth. We're going from the third maximum to the central maximum. Central to third, n would be what? Emily, n would be what? 3. Good. My wavelength is 630 nanometers. 630 times 10 to the minus 9 meters. If you're not sure what a nano is, that's okay. On your data sheet, it gives you all those prefixes. I think we're good there. Lambda is equal to d sine theta over n. Let's rearrange that to solve for d. Lambda times n over sine theta equals d. 630 times 10 to the minus 9 times 3 divided by sine 25 degrees. Make sure you're in degree mode, as always. We get 4.47 times 10 to the minus 6 meters. Now, 10 to the minus 6 is pretty common, actually, for a d value. Notice in question number 2, though, we had 10 to the minus 2. Like, dramatically different in question number 2, right? But also remember question number 2, we ended up with a wavelength that was 10 to the minus 3, right? Also a dramatically different wavelength. So when you have a dramatically different number from 1, you're going to have, that necessarily means you're going to have at least one other number that's quite a bit different from the norm as well. Let's do another example. This one's a little bit different. This one says monochromatic light, monochromatic, one color still. We'll deal with polychromatic light in just a few moments here, but for now, still monochromatic, one color. Shines through 1,000 line per centimeter. Diffraction grating produces a first order maximum, 32 degrees from the central max. What's the wavelength of the light used? This sounds like one of those double slit. We call them Young's double slit, named after Thomas Young, performed this experiment for the first time. This sounds like a Young's double slit experiment, but yet something's weird here. Usually we have 2 openings, 2 slits, 2 lines, and we measure the distance between those openings to get little d. Here we don't have the centimeters in between lines. Here we have the lines per centimeter. So what do you think this corresponds to? There's not 2 lines a certain number of centimeters apart. There's a certain distance with a certain number of lines per distance. This isn't d. This is 1 over d. Does that make sense? It's the inverse of d. It's not the centimeters between lines. It's the lines between centimeters. Now, we got 1,000 of these things. 1,000 openings per centimeter versus 2 openings total. We end up getting the same pattern, effectively the same interference pattern. The mathematics is the same. You just have to recognize that the value you're given here is not little d, but rather it's 1 over little d. So from that, you're going to get little d, and then just do your thing, whatever we did for the last couple of questions here. So what do we have given to us here? We're going to say 1 over d is equal to 1.0 times 10 to the 4 lines per centimeter. We're going to say that theta is equal to 32 degrees. We're going to say that n, because we just got theta, n is equal to what? First order maximum, central maximum, n would be 1. What's the wavelength? Okay, let's get d. If 1 over d is 1 times 10 to the 4, then d is going to be 1 over 1 times 10 to the 4. The easiest way to do that is take your calculator. 1 times 10 to the 4, right? 10,000. Flip it over, 1 over. Gives us 1.0 times 10 to the negative 4. But what units do we get there? Centimeters, which is 1.0 times 10 to the minus 6 meters. Does that make sense? Go to meters, but listen, don't convert lines per centimeter to lines per meter. Convert lines per centimeters to centimeters, and then convert it to meters. Why do we not want to find lines per meter right away? How do you convert centimeters to meters? Centimeters to meters is divide by 100, right? But if it's centimeters on the bottom, you're not going to times it by, or divide by 100, you're going to multiply by 100. So it's backwards, right? Let's get it on the top first. Let's get centimeters on the top, and then convert it to meters by doing what we always do, dividing by 100. Okay, what do we got here? Lambda is equal to d sine theta over n. Now it's just like all those other questions we had. D is 1 times 10 to the negative 6 meters times sine of 32 degrees, and we divide that by n, which is just 1. We end up getting a wavelength of 5.3 times 10 to the negative 7 meters. 10 to the minus 7 looks like I'm probably on the right track, right? Not always, as we saw when we went over the examples there, or the homework questions. It's not always 10 to the minus 7, but it usually is. Have a look at worksheet number 19 now. Number 5, 6, and 7, at least for the time being. I promised you a little while ago that we would deal with polychromatic light if we had more than one color. All the questions that we've dealt with so far, including the 3 examples and including the 7 or 8 questions on the worksheet that I've assigned to you, have involved monochromatic light, one color light. What do we do if we have more than one color? Well, the good news is I'm not going to give you any more practice questions just because we're starting to do polychromatic light. The good news is we end up solving it the same way. You just have to understand something as we go through it so that you end up solving it the right way. Okay? If we have, let's say, red laser light, monochromatic red laser light going through this 2 slits or this diffraction grating of 1,000 slits per centimeter or whatever the case may be, we will get a series of bright spots, dark spots, bright spots, dark spots like this. Okay, this is exactly what I've shown you for the last number of days. This is what we will get. If we have monochromatic light that is a different color, different frequency, let's say orange, then we will get a similar pattern. But there will be one difference, and that is the position of each of those maxima. If we look at the equation, lambda is equal to xd over n times L, then we see that lambda and x are directly proportional to one another. Lambda and x are directly proportional to one another. So in other words, as lambda is bigger, x is bigger. As lambda is smaller, x is smaller. All right, if we go from red to orange, I know that's not a very good orange, but it's supposed to be orange. If we go from red to orange, then that means the frequency is increasing. Red, orange, yellow, green, blue, indigo, and violet. The frequency is increasing, therefore the wavelength has decreased, right? If the wavelength has decreased, what would you expect to happen to the value of x, the distance between maxima? It would decrease. Well, take a look at this. It's not much different, but you do see a little bit of a difference here, right? These maxima for the orange are closer together than the maxima for the red. Now, we're still dealing with monochromatic. The first experiment, monochromatic red. The second experiment, monochromatic orange. But I just want to illustrate what happens if you have 2 different colors at different times before we look at what happens if you have 2 different colors at the same time. Okay, does that make sense? If we switch to yellow, we get a similar phenomenon taking place, right? Higher frequency, smaller wavelength still, and that means smaller x. So they're going to be closer together, and so on and so on and so on. Until you get down to blue and indigo and violet light, we're decreasing our wavelength even more. That means, Aidan, the value of x is going to be even smaller. Okay, so 5 different experiments here with 5 different monochromatic colors. 5 different monochromatic frequencies here. Make sense? What happens if I send all 5 of these through this 2-slit or this, this diffraction grating with 1,000 slits per centimeter or whatever? What happens if I send them all through at the same time? In other words, what happens if I have white light, which is all the colors, going through at the same time? Like I did over here in my poster, right? My Pink Floyd poster. White light goes through a prism. Well, now we're sending white light through this diffraction grating. What happens? Well, it will split it up. It will split it up as similar to what the prism did, but for a different reason. Instead of refracting at different angles, it will diffract at different angles. And it will split up white light, which consists of all of these colors, into individual colors: red, orange, yellow, green, blue, indigo, and violet, because each different color refracts differently, but it also diffracts differently. Now, take note of this, though. With refraction, red light refracted the least. Okay? If this is our central right here, our central maximum right here, we would say red light refracts the least, but red light diffracts the most. So it's opposite, right? Instead of getting Roy G. Biv, we get Vib G. Yor. The opposite of Roy G. Biv. Red light refracts the least. Blue or indigo or violet diffracts the least. Okay, so what is it actually going to look like if I end up putting white light through these 2 openings or through this diffraction grating? It splits it up, but it doesn't split it up to look like this. Right? You're not going to get one line of red, one line of orange, one line of yellow. Rather, these will be superimposed over top of one another. So what you end up getting is, here's a little bit of a simplified version of it, the handout that I just gave you here. You will get a central maximum that is white. It is all the colors together because it hasn't diffracted there. Now, your first order maximum, let's just look at the one side here. Okay, this is my central maximum, or as a number of 0 assigned to it, right? My first order maximum is this. It's not this one. It's not this one. It's both. My first order maximum consists of both of the colors. Notice that blue light diffracted the least, red light diffracted the most. Opposite to what we had with refraction. This is the first order maximum. Okay, then we have the second order maximum over here. Again, blue light diffracted the least, red light diffracts the most. Okay, realistically, what we often end up seeing is this white light with a rainbow here corresponding to the first order maximum, and then a rainbow here corresponding to the second order maximum. Why is it fainter? You guys remember that intensity graph, right? The further away you get, the lower the intensity. Okay, but it's still a rainbow, right? But it's a rainbow not Roy G. Biv, it's a rainbow Vib G. Yor, or backwards to Roy G. Biv. Okay, does that make some sense? Now, how do you deal with it mathematically? This is the important part here. Or, it's all important, but this is the part that ends up making this easier. If you get a problem where you've got multiple colors on your interference pattern, here's what I want you to do. Okay, look at the top diagram here. Multiple colors in this interference pattern. If you're given data for blue, then what I want you to do is pretend red doesn't exist. Like literally wipe it off the face of the map. If you're given data for blue, pretend red doesn't exist. If, on the other hand, you're given data for red, then wipe blue off the face of the earth. It doesn't exist. As far as you're concerned, it's dead to you. If you're given data for both red and blue, pick one. Pick one. Doesn't matter. If you're given data for both red and blue, pick one. I don't care whether you go with red or you go with blue, but don't ever try to do one of these diffraction interference problems with more than one color. Pick a color. And the obvious one to pick, hold on for 1 second. The obvious one to pick is the one for which you have data. If you have both, doesn't matter which one you use, but just use one of them. Now, just be careful here, quickly. Pick quickly before you pack it up. Look at this side again. Be careful. This is our central maximum. First order maximum. This is not the second order maximum. Okay, third order maximum, fourth order maximum. That's not what it is. This is the first order maximum. This is the second, because we're picking one color, blue. Or, right, because remember, red is dead. Or you could have said blue is dead. This is the first order maximum, and that's the second order maximum. But don't ever start counting all the lines and make them each a maximum. It's one color or another, and then go with it the same way as you dealt with all the other 7 questions on that worksheet.